there is a group structure on quadratic forms, right? Okay? No? There is a group structure, and this group structure is actually comes from multiplication of forms. Let me remind you. If you take f of xy and multiply it by g zw, then you have some other form f of some bilinear form of xy zw and some other bilinear form of xy zw.
Multiplication of, for example, matrix of bilinear, corresponding bilinear forms.
No, I don't really think this works like that. Okay, so still, the composition law gives you structure of a group on classes of quadratic forms, and genera are cosets of your principal genus inside the class group. Okay? This means that every genus contains exactly the same amount of classes. And you can actually...
Is it equal to class number?
What is equal to class number?
Number of classes or genus.
Number of classes in the genus is equal to class number divided by number of genera, right? By definition. Genuses. You see. Okay. So if every genus has one class, then the number is called convenient. Let us show that there are only finitely many convenient numbers. To show this, notice the following. If you have this, then the number of genera is equal to the number of classes, right? And what is the number of genera? Number of genera is an index of H inside kernel of KD, right? Рода. Есть род, а есть рода. По-английски genus and genera. Okay? So number of genera is equal to the index of H inside kernel of HD. KD, sorry. So what is this number? Well, kernel of KD is equal to phi of absolute value of D over 2, right? So exactly half of all numbers are quadratic residues. This is nothing smart. Now H is the subgroup of all squares that are invertible. Okay? This is due to the representability by principal genera, by principal form. Okay? H are squares. And how many squares do we have? Well, if D is equal to 2 to the alpha, P1 to the alpha 1, and so on, Pk to the alpha k, let's limit ourselves to minus 4 multiplied by some product here. Even some... let me explain this. If you have x squared plus ny squared modulo 4n, then this is the same as just squares. Proof. If y is even, then there is nothing to prove, right? If y is even, then you get just x squared modulo 4n, right? And if y is odd, then you have x squared plus n, where x is even, right? And x squared plus n is equal to n plus x squared. Okay? Because it's x squared plus n squared, which is congruent to n, plus 2nx, which is divisible by 4n. Okay?
So h is by squares?
H are just squares, everything that is square. Okay, how many squares there are modular d of the form minus 4 product sum primes? Well, you should be congruent to 1 modulo 4 and a quadratic residue modulo all these primes, right? So you get phi of absolute value of d divided by 2, which comes from 4, another 2 coming from p1, and so on. So you get phi of absolute value of d divided by 2 to the k plus 1. So number of genera is actually equal to 2 to the power of number of odd divisors of your d. Okay? And this is much, much smaller than square root of d. Should I explain why is this smaller than square root of d? Or everyone understands this? So let me write this down. G of minus 4n is equal to 2 to the omega 1 of n. And this is number of odd prime factors. Well, you see, there are possible prime factors 3, 5, 7. Let's exclude them. And for every other factor, you have 11, 13, and so on. For every other factor, 2 is at most 11 to the 1/3. So if you have g of minus 4n equal to h of minus 4n, this means that h of minus 4n is at most some constant multiplied by n to the 1/3. This is much, much smaller than needed, right? We know by Ziegel's theorem that it is at least n to the 1/2 minus epsilon. This means that there are finitely many convenient numbers. It is conjectured that actually that there are.
So this index is less than square root of d, and this last part.
So we know that class number is large always, and we also know that number of genera is actually small.
We know that class number is greater than what?
Ziegel theorem gives you C of epsilon multiplied by n to the 1/2 minus epsilon. So you can take epsilon to be something egregious like 1 over 100. And then you get a contradiction, right? Okay? Conjecturally, there is a complete list of ideal numbers. The largest of them is 1848. And it is known that there are at most 2 other convenient numbers. But it is not known whether there are actually at least one. It is conjectured that this answer is no. So
And there are no bounds.
there are, of course, no bounds because of the ineffectivity of the theorem. And okay, so my time is up, but I also would like to at least mention Bhargava cubes. Let me show you. This is a very fun way of thinking about the composition of quadratic forms. So let me explain. Once again, let me write down the multiplication structure on the set of quadratic forms. If you have two quadratic forms, say you have f of xy is equal to ax squared plus bxy plus cy squared, and g of xy is equal to a prime x squared plus b prime xy plus c prime y squared, then the composition works as follows. You take f of xy to be equal to a prime x squared plus capital B xy plus capital C y squared. Here B is congruent to B modulo 2a. B is congruent to B prime modulo 2a prime. And B squared is also congruent to D modulo 4a prime. It turns out that if your forms are sufficiently primitive, I mean, if there are some conditions on greatest common divisors, then you can find such a B, and of course, D is a discriminant. You need to, the composition of forms is only defined when the forms are of the same discriminant. Okay? And of course, C is such that the discriminant is equal to D. So C is B squared plus D over 4a minus D, or over 4a prime, right? Something like that. Okay, so of course, this definition is rather strange.
It is not with group structure in quadratic forms.
Why? This is a group structure of quadratic form. Composition law means that you get two forms, you form a composition, and this composition is, gives you a group structure on the set of classes.
But it's not a group structure.
Why?
It's the same.
It's a group structure on the classes, of course.
Before we gave a group structure for quadratic forms.
Yeah, this was a quadratic structure induced from the ideals. I tell you that you can rewrite this structure in terms of coefficients. And the formula is a bit unpleasant, okay? And I would like to tell you another way of looking at this stuff. This is a discovery of Manjul Bhargava, who observed the following thing. He worked with the following structure. He worked with just Z2, tensor Z2, tensor Z2. Okay? This is a Z module of rank 8, right? And this Z module can be interpreted as a set of cubes of integers. But cubes not in the sense like n multiplied by n multiplied by n, but in the sense of the following picture. A, B, C, D, E, F, G, H. And when you have a cube, you can produce 3 integral quadratic forms. How do you produce integral quadratic forms? You see, when you have a cube of integers, you have 6 2 by 2 matrices, right? Do you see 6 matrices here? So say M1 is equal to ABCD, N1 is equal to the opposite EFGH, M2 is equal to AECG, N2 is equal to BFGH, M3 is equal to AEBF, and N3 is equal to GHCD.
How ABCD, etc. corresponds to the basis of Z2?
So you have two basic vectors, E1 and E2, and you can take EI, tensor EJ, tensor EK, right? This is the basis of your tensor product. It contains 8 elements. That's it. Right? No?
Yes. And these are 3 coordinates.
These are 8 coordinates with respect to this basis. You can figure out the details yourself, please. You are welcome to do this. Что? Порядок важен? Yeah, the order is of course correct, but you can, for example, connect your two basic elements with an edge if they have an intersection, right? Or something like this. No. It's wrong. But if they only differ by one element. So this will be 1, 1, 1, this one, say 1, 2, 1, this. Okay, so you get the point. Okay, now on this set of matrices, you can act by the product of SL to Z multiplied by SL to Z multiplied by SL to Z. The following direct product acts on this set of matrices. How to act by ith component? Ith component maps Mi and I into, say, if you have RSTU, you get RMI plus SNI plus, comma, TMI plus UNI. Okay? So if you want to act by SL to Z on ith component, you do this with your ith pair of matrices.
What is these are coefficients?
These are coefficients of your matrix. So
we act on the pair or we act
on the whole cube. If you want to act by identity multiplied by identity multiplied by some matrix, then you take the third pair of matrices, you do this transformation, and that's it. Okay? And you can act independently by all the components, and these actions will actually compute. Now, if you have this 3 pairs of matrices, you can produce 3 quadratic integer quadratic forms. Okay? 3 integer quadratic forms are as follows. Qi of xy is equal to minus determinant of mix minus niy. Okay? So this is of course very, very mystical. Now if you act on these 3 forms using your action of cube of SL to Z, then action of say on say first component will transform your first quadratic form into the equivalent form, obviously, and all other forms will stay the same. because the corresponding operations of matrices will only do either row operations or column operations. So determinant will be unchanged. Very nice, right?
Could you, so we act on these cubes by product of
Of SL to Z on SL to Z on SL to Z.
yes, and
If you only act on the first component, so you act with M times E, then the first form will be transformed to the equivalent form, right? And the next two forms will be unchanged because
we
of
act by
because we act by on the first form by change of variables essentially, and we act on other two forms by doing row operations inside your matrix. Okay.
Can we interpret this action on the cube just by that we just take the first component of that we have the product of three copies of SL to Z, and we can just take first matrix and act on the first tensor, and the second matrix acts on the second tensor, and
Not really, right?
or it's not the same as just this.
I don't really know. Maybe you are right, but I don't really see this right now. Okay. Okay. So what is the next Bhargava's observation is that it turns out that all the discriminants of this of these quadratic forms here will all be equal to each other. You get three quadratic forms of the same discriminant. Okay? And this is also not all. Actually, Bhargava also was able to prove the following cube law. Class of Q1 plus class of Q2 plus class of